I'm Zachary Chilton.
And I'm Bradley Olbrey.
And this is arc length. But what's the definition of arc length? The definition of arc length is the approximation of the length of a function from x values a to b using an infinite number of chords whose 2 points intersect the curve within an infinitesimally small distance from one another. It is most useful when the total segment being measured is nonlinear, as it is an extension of the distance formula typically used for linear functions.
Arc length of a normal f of x function. The equation for arc length s is s equals the integral from a to b of the square root of 1 plus f prime of x squared dx. Remember that in order to obtain the arc length of a function f of x, the function must be continuous and differentiable from a to b.
Example problem number 1. For example, in order to find the arc length of the function f of x is equal to x squared, the first step would be to take the derivative, or f prime of x is equal to 2x. Following this, the next step would be to plug the derivative into the arc length formula using necessary bounds, for example from a is equal to 0 to b is equal to 2. The result is shown below, being s is equal to the integral of 0 to 2 of the square root of 1 plus 2x squared dx. The integral is then solved in order to get s is approximate to 4.647.
Arc length of a parametric function. The formula for the arc length s of a parametric function is s equals the integral from a to b of the square root of dx dt squared plus dy dt squared dt. In this formula, the functions x of t and y of t must each be continuous and differentiable.
Example problem number 2. In order to find the arc length of these parametric equations, being x of t is equal to square root t plus 2 and y of t is equal to t cubed minus 1, the first step would be to take the derivative of each, being x prime of t is equal to 1 over t square root t plus 2 and y prime of t is equal to 3t squared, and then plug them into the equations with the correct bounds. For example, a is equal to 0 and b is equal to 2. S can be seen below. S can then be solved in order to get approximately 8.123.
Bonus. Arc length of a polar function. In order to find the arc length of a polar function, this equation must be used with the correct limits. S equals the integral from a to b of the square root of r of theta squared plus dr d theta squared d theta. Of course, r of theta must be continuous and differentiable.
Example problem number 3. In order to find the perimeter of one petal of the following polar function, which altogether goes from 0 to 7 pi, the polar equation being r of theta is equal to 3 times cosine 4 theta over 3 to the 5th, the first step would be to take the derivative, being r prime of theta is equal to cosine 4 theta over 3 to the 4th times negative 20 sine 4 theta over 3. Then plug r theta and r prime theta into the equation with the proper bounds for a single petal, say a is equal to pi and b is equal to 2 pi, with s being shown below, and then solve for s is approximately equal to 31.106.
Example problem number 4. Real-world example. In order to find the distance an object has flown through the air, the first step would be to derive an equation using quadratic regression that represents the trajectory of the object, as shown here. This equation is f of x equals negative 0.187x squared plus 1.681x plus 0.255. The derivative is f prime of x equals negative 0.374x plus 1.681. Plug that into the equation to get s equals the integral from 0.157 to 8.88 of the square root of 1 plus negative 0.374x plus 1.681 squared dx. With this, s is approximately 11.729. But that's not all. The takeoff and landing points are approximately 8.723 units apart on the graph, equivalent to approximately 40 yards in real life. We just figured out that the trajectory is around 11.729 units long on the graph. So the last step is to set up a proportion, x over 40 equals 11.729 over 8.723, and solve to get the arc length. X is approximately equal to 54 yards.
Example problem number 5. In this example problem, the equation will be derived using quadratic regression on points plotted along Luffy's arm, with Luffy being the character in the following picture. This will allow the learner to have a visual aid in addition to the equations and formulas taught. The before mentioned character named Luffy can now be seen in the picture shown. The first step of the regression being drawing a grid and then plotting points along the curve, which is his arm. We then use quadratic regression in the points plotted in the last slide to create an equation to represent Luffy's arm. The equation being f of x is equal to negative 0.035x squared minus 0.005x plus 4.957. The derivative of the previous equation is f prime of x is equal to negative 0.070x minus 0.005. Then plug that into the formula with the proper bounds, being a is equal to 1.523 and b is equal to 8.2. With s being explained below that, we can then solve for s, or Luffy's arm, to be equal to 7.115 units. Given that Zach's positioned height, or 139.7 centimeters, is 75% of his normal height, or 185.42 centimeters, and Luffy's normal height is 172 centimeters, we can find that Luffy's positioned height is about 130 centimeters. Given that Luffy has a height of 130 centimeters and is 2.5 units tall in the picture, and his arm was calculated to be 7.115 units long, we can set up a proportion to find the length of Luffy's arm in centimeters, the proportion being x over 130 is equal to 7.115 over 2.5. Therefore, Luffy's arm must be 370 centimeters long. But wait, his arm goes into the background, right? The current image is what we called our Luffy documentation, or what we wrote up to set up a 3D perspective to measure the actual length of Luffy's arm, as it is a 3D object in the image. The reference used was Luffy's position height. And after counting all the Luffys generated by setting up a proportion through the shrinking of Luffy's arm as it passes into the background, with 6.33 Luffys at 130 centimeters per Luffy, we get that the length of Luffy's arm in this picture is actually 822.9 centimeters, which is also about 27.5 feet long.
In conclusion, we have reviewed how to find the arc lengths of regular f of x functions, parametric functions, and polar functions, completing practice problems on each one, a real-world example to further understanding, and a one-piece example just for fun.